In this video, I'm going to show you some more examples of homogeneous differential equations. First, let me remind you what is a homogeneous differential equation. If we can write a differential equation in the form of y prime equals to f of y over x, then we say the differential equation is a homogeneous first-order differential equation. So every homogeneous differential equation can be written in this form. And if you remember, for solving homogeneous differential equation, we use this substitution. We suppose v to be y over x, and from here y equals vx, which if we take derivative from both sides of this relation, y prime equals to v plus x v prime. Note that for finding derivative of this, we use product rule. And so y prime derivative of y equals derivative of this, which we can get to this relation. And then if we substitute y prime here with v plus x v prime, and we substitute y over x with v, then we can convert a homogeneous differential equation to a separable differential equation. This is the way that we can solve homogeneous differential equation. Let us start with our first example. The first example that here we want to solve is x plus y dy plus x minus y dx equals 0. First, we try to write the differential equation in this form. Y prime equal a function of x and y. To do so, I move this term to the other side of the equation. So I keep this here in the left side. So we have x plus y dy equals to negative x minus y dx, which if we apply this negative in the bracket, instead of writing negative x minus y dx, we can write it as y minus x dx. Now, if we bring this x plus y to the denominator here, and if we bring dx to the denominator of dy, we have dy over dx. Note that dy over dx is y prime. Dy over dx equals to y minus x over y plus x. But here, this step, maybe you think, doesn't seem that this differential equation to be a homogeneous differential equation. Because in a homogeneous differential equation, we expect to see something like y over x. But here we don't have any y over x on the right side of this equation. So how we can guess that this differential equation is a homogeneous differential equation? This is a problem. And if you cannot figure out that this differential equation is a homogeneous differential equation, you cannot solve it. So the first thing that is important in solving a differential equation is to be able to figure out the type of a differential equation. And this is a very important step. Whenever you write a differential equation in the form of y prime, as here dy over dx is y prime, equal to a fraction, which like this question. So whenever we have a differential equation in the form of y prime equal to a fraction, some terms in top, some terms in bottom. Similar to here, in numerator we have y minus x, in denominator we have y plus x. How we can find that the differential equation is a homogeneous differential equation? You have to look at the terms in the numerator and in the denominator. If all the terms, it's very important, if all the terms in the numerator and in denominator have the same degree, then we say the differential equation is a homogeneous differential equation. Let me show you this by some examples before we solve this question. For example, y prime equals to x squared plus y squared over x squared minus 2y squared. If you look at the numerator, every term in numerator is degree 2 and every term in denominator is also degree 2. The degree matters. And because the degrees of the top and the degree of the bottom are the same, note that all the terms must have the same degrees. So this is an example of a homogeneous differential equation. Another example, look at this one. X to the 3 plus 2y squared x over y to the 3 minus x to the 3. This is another example of a homogeneous differential equation. Every term in denominator is degree 3. This term is degree 3. But maybe this term is a bit confusing. Note that by degree I mean when x and y multiply by each other, add the powers. I know we cannot add the powers when the bases are not the same. But here, when we say degree of a term, we mean the sum of the degree of x and y. If x and y are multiplied, add them up. So this degree is 2, this degree of x is 1, 2 plus 1 is 3. So this term is degree 3, the other term is degree 3. So every term in numerator is of degree 3 and every term of the denominator is of degree 3. So the differential equation is a homogeneous differential equation. So again, if all the terms in numerator and the denominator have the same degree, then the differential equation is a homogeneous differential equation. Let's back to our question. In our question, the degree of y here is 1, the degree of x is 1, the degree of y here is 1, and the degree of x is 1. So because all the terms have the same degree, so the differential equation is a homogeneous differential equation. And so for solving this differential equation, we can use this substitution. And if you want to see this y over x more clearly in this differential equation, let me show you how you can make y over x appear in here. It's not necessary, but let me show you before I continue solving. If we divide numerator and denominator of this fraction by x, so if we divide numerator and denominator of this fraction by x, if we divide y by x, we have y over x, and if we divide x here, we have minus 1. And if we divide this y by x, we have y over x, and if we divide x by x, we have plus 1. And now you can see y over x here and here. Now it is more obvious that this differential equation is a homogeneous differential equation. Let's back to our question. So we get to this point, dy over dx is y minus x over y plus x. Now for solving this homogeneous differential equation, we use this substitution. So we suppose v to be y over x. And from here, y is x times v. If we multiply x by v, we have vx or x times v. Which from here we can say y prime or dy over dx equals v plus xv prime. Now if we substitute this y prime with v plus xv prime, we have v plus xv prime equals to, if we replace this y with xv, we have x times v minus x over x times v plus x. Now if we look at the numerator and denominator, we can factor x in numerator and we can factor x in denominator. If we factor x in numerator, we have v minus 1, and in denominator we have v plus 1, which if we cancel x with x, finally we can simplify this as v minus 1 over v plus 1. Another way that we can get to this is to note that if we divide numerator and denominator of this fraction, as I showed you earlier, with x, if we divide numerator and denominator by x, we have y over x minus 1, y over x plus 1. Y over x is v, so we have v minus 1 like here, and v plus 1 in denominator. Let's continue solving. Now here, if we move this v to the other side of the equation, so we have x v prime equals v minus 1 over v plus 1 minus v. Now here, if we do a common denominator, the denominator of v is 1. Let me show you how we can get common denominator here. It's clear that the common denominator is this, v plus 1. We write numerator here, and now we have to multiply this by this. V times v is v squared, but don't forget you have to put a negative here, and v times 1 is negative v. This v and this v cancel each other, so finally we have negative v squared minus 1 in numerator and v plus 1 in denominator. So after simplifying this, we get to this expression, negative v squared minus 1 over v plus 1. So we have x v prime equals negative v squared minus 1 over v plus 1. Now here, if we replace this v prime with dv over dx, and if as usual we separate v from x to make the differential equation a separable differential equation, we get to this. Let me continue from here. dx, actually let's write it the other way, v plus 1 over v squared plus 1 dv equals to negative dx over x. Note that we bring this up when we move it to the right. So v plus 1 goes here. And if we keep negative here, if we factor a negative in numerator, and we keep negative in the right side, and we just move, if we factor negative, we have v squared plus 1. So we only move this to the denominator of the left side. So we have v squared plus 1 here. And then we move this dx up and we bring x down. This is what happened, and we will get to this expression. Now, the differential equation is a separable differential equation. For solving this, we have to integrate from both sides of this equation. So we have to integrate this and integrate this. Integral of the right side of this equation is clear. Integral of dx over x is ln of x. But finding this integral is a bit tricky. Let me show you how we can find this integral. Integral of v plus 1 over v squared plus 1 dv. First note that we can write this as v over denominator plus 1 over denominator. So first I write this as v over v squared plus 1. So I separate numerator by denominator. Plus 1 over v squared plus 1. Note that this is the same expression. dv. Integral of this part is clear. This is one of the formulas of integral. We know that integral of 1 over x squared plus 1 dx is tangent inverse of x. This is one of the formulas of integral. So integral of 1 over v squared plus 1 is tangent inverse of v. But what is the integral of v over v squared plus 1? For finding this integral, we have to use a simple u substitution. Note that for finding this integral, if we suppose u to be v squared plus 1, the denominator is supposed to be u, then du is 2v dv. Unfortunately, we have v dv in numerator without this 2. So numerator is du over 2. 1/2 du. So this integral equals to 1/2 du over u. The denominator is u and the numerator is 1/2 du. Let me clear here. This integral equals 1/2 ln of u, but u is the denominator. So this equals 1/2 ln of v squared plus 1. So integral of this is 1/2 ln of v squared plus 1. So by integrating from left side, and the right side of this differential equation, we have 1/2 ln of v squared plus 1 plus tangent inverse of v equals negative ln of x plus c, which for a moment I prefer to write it as c1 because later I want to change it to another constant. Now, if you notice, we have a ln here in the left side, and we have this ln here. If you like, actually, you can leave the answer in this form and just replace this v and this v with y over x, which we have here. But actually, you can write this final answer in a better, shorter form. So we move this to the left side of the equation, and at the same time I want to multiply both sides of this equation by 2 to get rid of just this 1/2 here. So I move this to the left side and I multiply both sides by 2 at the same time. If we do so, we have ln of v squared plus 1 plus ln of x, but because we multiply by 2, here we have a 2, and because we multiply by 2, this 1/2 cancels with that 2, plus 2 tangent inverse of v equals to Because we multiply this by 2, it becomes 2c1. And now I name that 2c1 a new constant like c. Now we can combine this ln, this ln. How? First bring this 2 to the power of x. So we have ln of x2. And if we replace v here and here with y over x, so we have ln of y squared over x squared plus 1 plus 2 ln of x plus 2 tangent inverse of y over x equals c. Actually, let's write this as ln of x2 because now we want to combine these two. We know that ln of a plus ln of b equals ln of ab. This is one of the properties of logarithmic functions. Now if we use this property, we can write this as ln of the first expression y2 over x2 plus 1 times by x2. And if we multiply this x2 in the bracket, this x2 and this x2 cancel, and x2 times 1 is x2. So, combining these two ln's, we get to ln of y2 plus x2. Because we multiply this in this bracket, and x2 and x2 cancel, and x2 times 1 is x2. And this is the solution of this differential equation. At first, it seems that this differential equation should be an easy differential equation. But as you see here, it was a really tricky question. So the answer is ln of y2 plus x2 plus 2r tangent of y over x equals c. Let me write the final answer here. ln of y squared plus x squared plus 2 tangent inverse of y over x equals c. Now let me show you another example. The next example is this: x dy over dx equals to y plus square root of x squared minus y squared. And also we have an initial condition in this question: y at point 1 equals 0. First, we divide both sides by x to get rid of this x, to make the differential in the form of y prime equals something. By dividing both sides of this equation by x, we have dy over dx equals y over x plus square root of x2 minus y to the 2 over x. But note that we can write this in this form: a square root of x2 minus y2 over a square root of x, because a square root of x2 is x. Note that here we suppose x to be positive, and note that in the initial condition also x is positive. Because in general, square root of x2 is not equal to x. We know that it is equal absolute of x. But here, if we suppose x to be positive and our initial condition is also positive, it's completely safe to suppose x to be positive. Anyway, so My idea here is to bring this to the inside of the radical to make it simple. So anyway, if we write this x as radical x2, and if we combine these two radicals now, we can write it as x2 minus y2 over x, which if we now separate the numerator by the denominator, we can write it as x2 over x2 is 1 minus y2 over x. So we can write this radical over x as this. My idea was to make something like y over x appear in my differential equation. So finally we can write this as dy over dx equals to y over x plus radical 1 minus y2 over x. Now it is more clear that this differential equation is a homogeneous differential equation. And if we write this as y over x, it is much better. Now for solving this, as usual, we suppose v to be y over x. From here y is xv, and from here y prime is v plus xv prime. Now if we substitute this with v plus xv prime, don't forget y over x is v, so v plus square root of 1 minus v squared. Replace this with v also. Now this v and this v cancel from two sides of the equation, so we get to this xv prime equals square root of 1 minus v squared. Let me write the equation here. X dv over dx equals to square root of 1 minus v squared. Now if we bring this to the denominator of dv, and if we bring dx up as usual and x down, we can separate x and v. So we have dv over square root of 1 minus v squared equals dx over x. If you remember from the integral formula, integral of dx in general over square root of 1 minus x2 is sine inverse of x. So this integral is sine inverse of v. Sine inverse of v equals ln of x plus, again here I suppose x to be positive. And now, if you like, you can get rid of this sine inverse by taking sine from both sides. So v equals sine of ln of x plus c. And don't forget, v was y over x. So y over x equals sine of ln of x plus c. Finally, y is x times by sine of ln of x plus c. Now we can use this initial condition for finding c. Based on this initial condition, if we plug in 1 for x and 0 for y, we have 0 equals to 1 sine of ln of 1 plus c. ln of 1 is 0 and sine of c is 0. When sine of c is 0, we can say that c is 0. Again, we get to something like this with the initial condition, which from here c is 0. So, because from this initial condition c equals 0, so the final answer is x sine of ln of x. Now let me show you another example. X times y minus x y prime equals y squared. As the first step, we isolate y prime. So we divide both sides by this to get rid of the coefficient of y prime. So we have y prime equals to y squared over x times y minus x. Now note that in numerator, the degree of this term is 2. And in denominator, if you multiply x in the bracket, we have xy minus x. The degree of this term is also 2. And the degree of xy is also 2, because x to the 1 times y to the 1. If you add the degrees, it's degree 2. So all the terms in numerator and all the terms in denominator have the same degree. So this differential equation is a homogeneous differential equation. And so for solving this, we can use the technique of homogeneous differential equations. So we suppose v to be y over x. Y is x. And from here, y prime is v plus x v prime. The same process again and again happens. We replace y prime with this. So we have v plus x v prime equals 2. Note that here we can replace y with xv, so y2 is x squared v squared. And in denominator we have x times y is xv again, x times v minus x. Note that here we can factor x from the bracket, and we can bring that x out and multiply by this x, which if we do so, we get to this v plus x v prime equals x2 v2 over x2 times v minus 1. So we factor x from this and this. We bring x here and we multiply by x, so we have x2. Now x2 and x2 cancel. So we have v plus x v prime equals to v squared over v minus 1. Again, we bring this v to the other side and we simplify the right side. So we have x v prime equals to v squared over v minus 1 minus v. If we do common denominator for this, v squared over v minus 1 minus v over 1, the common denominator is v minus 1, v squared minus v squared plus v. Don't forget, when you multiply this v by this v, don't forget this negative. V times v is v squared, but don't forget negative v squared. V times 1 is v, but negative times negative, positive v. So finally, after simplifying this, we have v in top over v minus 1. So we have x times dv over dx. We replace v prime with dv over dx equals v over v plus 1. Minus 1. Don't forget, here is minus. Here we have minus, here is minus. Now, as usual, if we separate x from v, we bring v down, we bring this up, as the previous examples. So finally we get to this v minus 1 over v dv equals to dx over x. Integral of this is ln of x plus c. But what is the integral of this? For finding integral of v minus 1 over v, note that we can write it as v over v. We separate numerator by denominator. V divided by v minus 1 over v. This is the same expression as here. V over v is 1. So we have 1 minus 1 over v. Integral of 1 dv is v, and integral of 1 over v is ln of v. So this integral of this equals to v minus ln of. Note that here we have a separable differential equation. For solving separable differential equation, we take integral from both sides. Integral of the left side is this, integral of the right side is this. Now here, because this term and this term have ln, we can bring this ln to the right side to combine ln's. Or if we don't like to do extra steps, you can leave your answer in this form. Just replace the v's here with y over x, and that's your answer. But if you would like to make your answer shorter, better form, you can do these steps. It's up to you. So we keep v here. We move ln of v to the other side. We have ln of v plus ln of x plus c. Let's make this c1 because later I want to change that. So finally v is y over x equals ln of y over x plus ln of x. But note that if we combine these ln's here, this ln with the other ln, we can write it as ln of y, because ln of a plus ln of b is ln of ab. We can multiply the expression. If here we multiply y over x with x cancels with x, so finally we have y over x equals ln of y plus c1. And this is the solution for the differential equation. But if you want to write your answer in a better form, you can do these extra steps. First, let's move this c to the other side of the equation. So we have y over x minus c1 equals ln of y. Again, I'm saying you can leave the answer here, and that's the final answer. It's completely fine. But if you like, you can do these extra steps, and it is not necessary to do these steps. Now, to get rid of this ln here, we can use this rule. If ln of a equals something, note that here this is a and this is that something b. If we have ln of a equals b, a equals e to the b. We know this rule. So to get rid of this ln here, we can say y equals e to the y over x minus c1. But we can write this as e to the y over x times e to the negative c1. The base are the same. If you add them, you can get the same thing. So now here, this e to the negative c1 is a constant. E is constant, c is constant, c sub 1 is constant, so everything here is constant. So you can name this as c. So finally, y equals to c e to the y over x. This is another form for the solution of this differential equation. So this is one form of the solution. This is another form for the solution. I hope by watching these extra examples, you have learned completely how to solve homogeneous differential equations. If you like this video, please subscribe in my channel. See you in the next videos, and thank you for watching.